one warning from the start. This might get a bit mathematical if you don't understand something in detail. That is to be expected. I'm just giving a quick overview of one algorithm that I find very interesting. It's a bit of a segue from standard economic design, which focuses more on linear programming, particularly integer linear programming. And this uses a mechanism that's more commonly seen in machine learning. Somebody who has used adaptive boosting might know this already. But let's start off with the motivation for why we might be interested in this to start with. I think we're going to hear more about that later. But what gets me interested in post-capitalism is mostly the amount of friction losses in standard markets. Some people might have heard of information asymmetry, the idea that information in for-profit markets is often deliberately not shared. If I buy a shirt, it's almost definitely going to be advertised as premium or deluxe. It's not going to be advertised as low quality, even if that might be accurate. And that gives me, as the consumer, limited amount of information to make decisions. And that means some utility, if we want to count it in that way, is going to be lost. We also have coordination problems, which is the game theory equivalent of this, that something might be optimal for a group, but it's suboptimal for each person individually, like adjusting for climate change for profit companies. And these problems just aren't solved. Like we didn't adapt to COVID, we didn't adapt to climate change globally almost at all. And there's also the concern that we have unequal access to goods and resources, particularly on a global scale. I'm going to skip over the centralized planning. I think we can talk about that in discussion and get into what resource sharing actually is. The idea comes from the multi-commodity flow problem, where the trivial example, I think, is think of a group of passengers that start off at different cities and they want to get to particular cities. Obviously, we can't just send them to random cities. Each person, like if one person wants to go to Bonn, we can't just send them to Munich. Each person has their own individual goal. So the flows are all distinct, but these compete for the rail lines. One train might also only have capacity for 30 people. If we put in 50 there, we're going to have a problem. Resource sharing generalizes this to not just graph problems, but all kinds of problems. It's used effectively for fairly large problems where we have over a million, like many millions of goods, many millions of consumers. If you imagine putting this in a matrix, it would get rather large. Why think about this in the sense of economic planning, where I haven't seen it before? Because it's principally a coordination or conflict resolution algorithm. Consumers are all treated equally, which can be changed, I think, but it's the default. It's very simple, which is why I'm presenting it here. There are other algorithms that I also find interesting. Maybe we can talk about that later too. And it's highly modular. It kind of defies or doesn't defy centralization, but it doesn't require it. We can essentially outsource the decision-making process to each individual consumer. It doesn't have to be linear, it doesn't have to be convex. We actually don't make any demands of it at all, with very few exceptions. And one example I would give here is the idea that like this is how it's actually used in practice right now for chip design, like computer chips. If we have a bunch of different small circuits on a larger chip, we have to wire them together so that the outputs of chip A arrive at chip B. And these nets can get rather numerous. We're thinking of many millions of nets on a modern CPU, for instance, and they can't overlap, or at least they can't overlap on the same layer. Usually we have up to 10 layers where we can route these. But if wires cross, obviously we're going to get cross communication. That's going to break our circuit. So we need to first approximate the shortest of these Steiner trees, which are just essentially pathing trees between these end nodes, which are the white circles, and then we can add new nodes in the middle. These are Steiner points in the black, and then route these together. And in chips, these would all only go vertically and horizontally. In practice, we don't really care. We approximate these, and then we find some kind of overlapping of these that doesn't cross more than 6 to 10 times, depending on which architecture we're using. This is the algorithm. If this looks eldritch to anybody else, don't be alarmed. This is how any bond student feels as well when they see it the first time. So I'm going to translate it to English. The inputs are essentially a resource set, and this is just a number. If we have like 10 customers or 10 consumers, we would just enter 10 as the set. Each consumer gets an index. We don't really care how they're sorted. This is just in order to keep track of which resources we have. And we have a set C of consumers, and these are essentially the people who can make demands of our system. For each consumer, we have an oracle. Oracle is a function that we don't make any demands of in particular. And this is the decision-making process, essentially. We are presenting the consumer with a set of prices for each resource. And we want the consumer to make one decision that is of the lowest cost. And in this case, it doesn't have to be perfect. It only has to be maximally twice as expensive, or sigma times as expensive as we would want to be. In practice, that would be 2. I'm going to work with 2 here. Obviously, we can enter any number we want as long as it's slightly larger than 1. We can see that this vaguely resembles an actual market. Like if I want to buy something, if I already have a goal in mind, I'm going to obviously pick the cheapest option that satisfies my desires. And I might not always get the cheapest. Like anything I do in real life is going to be an approximation. If I want to find the cheapest shirt, I'm not going to check like 10 million shirts on AliExpress. I'm going to buy one that is close to me that maybe I can touch, so I don't spend too much time on the decision. The output now, given that we have access to all kinds of consumer decisions, is a combination of consumer decisions that minimizes the maximum resource usage. It's a min-max algorithm. So we have one resource that is essentially the bottleneck. In the train example, there might be one track that is used as like 90% capacity and all others are lower. So we would want this to be 90% and not 91. In the approximative case, obviously, we have to compromise here. We might also use sigma here again, but then we have the disadvantage that we might oversubscribe. So if we're at 90% utilization in the most effective case, we would be at 180% usage in the approximative case. That's going to be a problem. Another problem is some people might have noticed the convex sign, or the conv function at the top. That means we're choosing from the convex hull. Essentially, we are choosing partial combinations. That doesn't always make sense. If I want to request a vehicle and I get 50% of a car and 50% of a bicycle, I have 0 vehicles. So sometimes we have to solve these partial solutions and translate them into integral solutions, but that can actually be done, and I give some resources about how we would do this in practice. This is the planning part, and we're going to see in a bit that this is essentially the market over a large consumer set. So this is the algorithm. I don't expect you to understand it in 1 minute. I definitely can't explain it in 1 minute. I'm just going to give a rough overview, so maybe you will get the intuition of why this actually works. What we would do here is we would track how much are resources being used in the current stage. These are the alphas. This is essentially a vector that has one number for each resource we might use. We have the capital X, which is how much are our customers or our consumers being satisfied in the moment. And we have the lowercase x, which is the actual solution that we are assigning to each consumer. We don't actually need these. We could get them from the prices at the end, but that gets a bit more mathematical. And also we have a price vector. These are the y's, which is what we are pricing our resources at to incentivize consumers to make different decisions. What we would do now is iterate over t phases. T is a constant, often like let's use 10 here. That makes it a bit easy. And on each step, we would choose the step over t fraction of consumer demands and satisfy these. So to make it easy, in the first step, we would make sure that each consumer gets 10% of what they want. In order to do this, we request a choice from the consumer. This is in line 7. We assign one solution. This is a block, thus the B, from the oracle function. Then, and this looks a bit tricky on line 8, essentially what we would do is just find the increment that we're currently using. If we're having particularly large resource sets, this can get a bit tricky. If we're normalizing them all to 1 as like 100% of a resource, it gets very easy. So the idea is to increment up to, in this case, 10% of consumer satisfaction. We would assign the resources to the consumer. We would update how satisfied the consumer is with the result. We would update our resource usage, given that we have taken some resources from the pool. And now, and this is the important step and probably also the trickiest to understand on an intuitive level, we update the prices exponentially depending on how much our resource is already being used. And this looks rather small. If you imagine like e to the power of 0.1 isn't that large. We're doing this for all consumers. If you do this for 1 million consumers, Y is going to get big very quickly, and future consumers will have a lot of incentives to avoid the resources that have already been assigned before. The runtime looks rather ugly. The idea is just that this is roughly linear. Like we have T times C Oracle calls. For each phase, we have to query all customers. We also have some like the plus R is basically how numerically stable is this. If we're using like very strict rounding rules, the algorithm will get slower. But the logarithm and the linear factor here don't matter as much as the phase times consumer first part. The literal runtime gets a bit ugly because we actually use 3 constants. These are used for some sort of fine-tuning to make sure the algorithm works with the scenario we have. Some are a lot stricter than others. Sometimes we only have like 10% of slack. Sometimes we have 50% of slack in terms of how many resources we actually need for an ideal solution. But essentially, this is σ-approximate, and it has sigma polynomial runtime. If we have a very if we want to make our algorithm like 50% quicker, it's going to be 4 times slower, given that sigma occurs twice in the runtime at the bottom. In practice, I think we would use a number of 2 for chip design, but obviously we can change these, and often these are used iteratively, where the first time you're just figuring out how strict are the bottlenecks in the example we're using, and how much time do we have to calculate the results. The takeaways for me here are that the algorithm essentially simulates a fixed supply market. Like we are giving consumers choices. Each time a choice is made, the price levels shift, and then future consumers can make different choices. One aspect that I find more pleasing than with actual markets here is that it's A, all simulated, can be very fast, and B, there isn't as big of a first mover advantage. We can randomize the consumers, and also remember that we have many phases. It's not like Black Friday in the US, where if you're first in the store, you get all the PlayStations and I get 0, but you only get 10% of the PlayStations, even if you can afford them all. And if we choose T as 100 or even larger values, we can optimize for this even more, even though in practice there are probably smarter ways to go around this. Limitations here are that all consumers weigh the same. That might not always be the case. Sometimes it's better to have a partial solution than to have no solution at all. If we're using this in a distributed way, we have to make sure that consumers are actually trustworthy, which goes back a bit to the incentive problem that is often ascribed to socialism. I don't think this is unsolvable. I also don't think it's as easy as some socialists make it. Making sure that factories correctly measure their in and outputs is tricky, and making sure that consumers don't oversubscribe or exaggerate their inputs is also tricky. I think this might be more useful as like one smaller part in a larger algorithm that sanitizes inputs and outputs to make sure that these kind of abuses don't happen. Something I mentioned before is that convex combinations don't always make sense. I can't get 50% of a train ticket, for instance. In practice, we would just randomly round them. This is kind of similar to how we deal with integer linear programming. It has better performance guarantees, though. I've linked a paper in the back for anybody who wants to read up on this in more detail. I I mentioned oversubscription of resources. If we have a particularly tricky case where even the ideal solution is already close to the limit, then our approximate solution is almost always going to get above it. Then we can, we could run the algorithm again with a smaller sigma, of course. But if that would take too long, we might just have to adjust our resource inputs. Like if we're dealing with soft targets, which I think are most of the targets we're facing in practice anyway, such as labor pools or environmental goals. Like if we can't reduce carbon emissions by 50%, maybe at least we can do 45% or 49%. Approximative quality might still be useful in a lot of cases. And I think with resources, this is usually the case. The last point that I didn't get into is numerical instability. If the prices get very, very large in the optimization part, there are some instability problems that we have to take care of, but there are also algorithms designed to adjustments to the algorithm designed to solve this in practice. I've also linked a paper in the back for those who want to read up on this in more detail. Applications I could foresee for resource sharing outside of just intra-organizational chip design, for instance, would be large logistics planning. And I'm thinking more road networks than rail networks, particularly if we have a lot of endpoints and standard linear programming kind of grinds to a halt if the matrices get too large. Though it's questionable, maybe that can also be improved in the future. What I find also interesting is like more stakeholder conscious economic planning, where we have both physical consumers and like simulated consumers that are used to manifest, for instance, environmental or ethical guidelines that also have demands, but their demands aren't goods, but particularly anti-goods, for instance, pollution or resource depletion that need to be avoided. This can be modeled very easily because none of these have to be linear. There can be any kind of function. Ideally, they should be continuous in some sense, but we can just put in any consumer function that we want. We could also use this kind of backwards for bottleneck discovery. Some people already mentioned before that like counterfactual planning or counterfactual reasoning is going to should be a large part of economic planning. And I agree. Sometimes it's very useful to forecast how things could go wrong, and this algorithm will easily show where bottlenecks lie in an economy, which parts would break the easiest, particularly if we jiggle the inputs and outputs around a little. Indicators that the algorithm would be useful are that all consumers must receive a satisfactory outcome. We can't just ignore some and maximize utility somewhere else. The submodules, so the Oracle functions, are all trustworthy. None are going to request 90% of all resources just because they can. We can query them fast. Like if we have to call them on the phone, this might not converge in time. And this is slightly optional, but in tricky problems, we might have to be okay with mild resource oversubscription. And my conclusion for this would be that I really find this algorithm interesting because it seems almost universal. I have used this myself in real life. It can be adjusted to all kinds of different problems. Planning doesn't necessarily imply that we're dealing with matrices and mid-integer linear programming. Resources that we're using often are kind of fuzzy and vague. We don't have exact quantities of what we're using, and we can adjust quantities post factum if we need to. And this wasn't covered in detail here. I would highly recommend the paper Chip Design, that real-life planning for a complex system often involves iterative, approximate, dynamic, and kind of ugly algorithm, kind of like this amalgamation of different algorithms where we make a choice and then we make another choice and decide the first one wasn't actually that smart. We're going to change it now. This kind of deviates from what you might have seen in your undergraduate CS courses, where you're just using Dijkstra for shortest paths and you're done. This is more like making a tentative decision and then changing your mind later. And it outperforms most deterministic algorithms in practice. And that is something I find really interesting and think is also overused in these kind of planning environments. I'm going to share these slides later. I don't expect anybody to write this down now, but these are the papers I mentioned before. If anybody is interested in them or wants to ask questions about them, feel free to ping me. And that is it from me. And thank you all for your attention.